It's information. But in addition to that information, there is location. So it is both regular data plus this extra thing, location specific information, and then a lot of additional data that you don't see in in a table, but is encoded within that spatial data set. The information content of the data will change with the location because as you're looking at different countries, right, the information about that country is going to be different. On extremely rare occasions, spatial data may only include location, but that's so rare. I've never worked with that in reality. Um, uh, on a what you'd expect more often is your spatial data to be regular data plus that location option. And there's many different types of data for spatial data. It's really set up into two kind of worlds of data models. There's the vector data model, where we're going to represent things as points, lines, and polygons. And then there's the raster world where we are going to be using points, lines, and polygons, but based on some grid kind of setting. So when you look at satellite imagery is essentially um, grids of pixels, and each pixel has a different value. And how that value is communicated to you is how the raster data model emerges. Okay, so if you've ever looked at Google Maps, you might have the satellite view, but then you'll have the regular view. That will be the vector data model. So our work for this workshop will kind of focus primarily on the vector data model. A lot of health research will in epidemiology similarly works on the vector data. Um, and that's because we tend to work with people, and people can be a little bit easier to, or people, streets, buildings, those things can sometimes be easier to be represented as vector data. However, when you get into more environmental sciences and the physical and natural environment, that's where we start to see a little bit more raster data being used. That's kind of the big picture, but what's the smaller picture? What are we using for today? Well, we're going to work with tabular data or CSVs, comma separated values that can store spatial information, but they're not exactly spatial data yet. They need to be converted into spatial data. So here we can see a data set we'll be working with, methadone providers. Methadone is a type of medication for opioid use disorder. Um, and here we can see the health providers, the address, and then a longitude and a latitude. The longitude and latitude gives us information to convert this into spatial data. We're also going to be working with spatial formats like a shapefile, which is a proprietary data format made of at least 4 extensions. Or the original version was proprietary, but there are open versions as well. And then we'll also be working with a GeoJSON, potentially, which is an open standard format for encoding a variety of geographic structures. That's really been popularized by the Google developer cohort. But we will also work with a GeoPackage, which is another spatial data format that's considered very elegant and a bit cleaner than a shapefile or a GeoJSON. However, we tend to only see GeoPackages being used by spatial experts and specialists. So I'm just including it in some of your workshop materials so that you can see how easy it is to work with spatial data formats. However, figure out what works in your own community. So your team might be more familiar with working with shapefiles because you have a lot of traditionally trained GIS experts and so on and so forth. So just to show you how spatial data is regular data, here we are looking at point emissions in Illinois from the National Emissions Inventory. And the shapefile format is actually a group of files. So it's the .shp file, but it's also the dbf file, which is a table, as you can see here, a data table or database file. There's a projection, which is encoding the spatial, we'll talk about coordinate reference systems in just a little bit, as well as these other features that will help convert this data to the points that we see on the right-hand side. So what you're seeing here are two views, the spatial view of the data and the non-spatial view of the data, but it's all the same data. So with spatial data, we don't just do visualizations, we're working with regular data in a different dimension. And within R, we're going to be specifically working with the SF library. The SF library is the primary way to work with spatial data. So SF uses traditional R settings like data frame, like a table or two-dimensional array like structure. SF is also friendly with Tibbles, which is a modern reimagining of the data frame using the Tidyverse suites of packages. And then as well as SF objects, or simple features. And simple features refer to a formal standard that describe how objects in the real world can be represented in computers. So some PostGIS language, they'll also be using a similar standard. So a lot of the functions that we use in SF are not just for R. They go beyond R. It's an actual standard that's used globally across many different types of coding languages and scripting languages. And why are we using the R-spatial ecosystem? Well, it's a very positive, collaborative, active community. It's a growing community. It's online, it's social. If you have questions, there's a lot of folks throughout the internet that are eager to help and support. There's also multiple resources available. So I'll be highlighting this RGeoComp org one, but there's also these other um, sources that are available as well. And as you can see here, that over time, SF emerged and kind of rapidly overtook the other libraries as being extremely useful and highly used by different communities. So this text comes from the Geocomputation textbook intro. And so in chapter 1 of the toolkit, there's going to be a little bit of an overview of a spatial orientation. So feel free to read through that a little bit more in your own time. Um, Again, I'm trying to condense something that takes, months, years, into just a few minutes. So obviously everything we'll be talking about is a lot more complex and complicated. But what's really exciting about this world is that all that information is available and shareable, and you can kind of do that on your own time as you're scaling up your own skills and that sort of thing. So with that, and here I'll just, yeah, no, I'll stay on the screen. We're going to shift to probably the most important part of working with spatial data, and that is understanding what your spatial reference system is. So a coordinate reference system, we might use the term CRS, will communicate what method should be used to flatten or project the Earth's surface onto a two-dimensional space. So the Earth is round, and it's actually not even perfectly round. There's, it's rather lumpy, it turns out, as a geoid object. But as we turn this spherical object into two-dimensional space, there are hundreds, if not thousands, of different ways to flatten things. So imagine having an orange, take off the orange peel and flatten that orange peel, right? the peel is never going to look the same way that it did when it was, a sphere. Anytime you move from three-dimensional surfaces to two-dimensional, things will change. So different CRSs will imply different ways of projections and generate substantially different visualizations. And we'll show you a couple examples in just a minute, and there's more in the text as well. So in SF, there's two functions we'll be using a lot. You use STCRS to check what CRS you're working with. And then to transform from one coordinate reference system to another, we'll use ST transform. So here are an example of some very classic projections. So the Robinson coordinate reference system projection is something that we're all probably familiar with from around the world, but it's considered a compromised projection, meaning it's a little bit wrong there's errors in area preserved, distance preserved, and angles preserved from how you because every time you take again 3D to 2D, you're introducing some error potentially. So the projection or the way that we see the world is actually riddled with errors when you're thinking about it very technically. So you can just, for example, see how the continent of the Arctic looks dramatically different depending on which projection you're using. And that's really because of how, either angle, distance, or area is being preserved. So, for example, in the Robinson compromise projection, we can see that there's a lot of aerial distortion at both of the poles, and then there's also tremendous angular distortion, not just at the poles, but kind of spreading out across the rest of the surface. The only place that is going to have very little distortion on the Robinson projection will be if you're on the equator. And so here again, you can see that there's many other ways. The Lambert conic projection has the least distortion for area. However, that might not actually be very useful. So this is why we use projections in the way that we do. Even if they're not perfect, there are some that are more useful than others when we're doing analysis on a very small scale. So fortunately, a lot of the work we do is on a very, very small scale, a city, a state, even a country. That's considered quite small, considered in respect to the rest of the space. So here's one of my favorite projections, the Dymaxion projection or the Buckminster-Fuller projection. And it really takes that idea of, an orange, and you're opening it in a way to kind of minimize how things look. It's beautiful and very, minimizes a lot of error. However, not very practical at all for planning purposes or for research purposes and that sort of thing. So in R, you're going to need to define your coordinate reference system. And we do that using SRID integer. So that is a spatial reference system integer or identifier. And one of the most common code books that record all the different projections is the EPSG code. That initially meant the European Petroleum Survey Group. It's a comprehensive database that stores thousands of different projections. That being said, a lot of times when you're working with data that are point data with like latitude and longitude information, you're probably working with EPSG 4326. And long story short, the most important note when you're working with this projection is knowing that this is not a projection to use if you want to calculate distance. The coordinates are, the distance is degrees, not feet, not miles. So you can't just subtract, you can't just use, uh, you can't just take the 2 points and get the shortest distance between them because that will be the distance in degrees, and that degrees is a completely different metric than feet, miles, meters, kilometers, and so on and so forth. So usually we'll have to first acknowledge that the reference system being used is 4326, and from there we can actually calculate or transform into a different projection that uses feet or miles for additional analyses. So all of this probably will sound like a lot, and that's fine. That's pretty normal, actually. But it takes a while to work with this a couple times for it to start to click. Okay. So when you're trying to figure out what EPSG or reference system you want to work with, Google is one of the best ways to do that. So, for example, if I am working in Sweden, I would search EPSG Sweden and type that into Google, and you'll get a bunch of options right away that will give you, many different options for which EPSG to use. You'll look to see which distance metric is identified, and so on and so forth. So in our work, in our examples, we'll be working in Chicago and Illinois. So I would type in EPSG Illinois, and then I might type in feet or kilometers or something like that, because that will push up projections that are include distance as something that we actually work with, versus another option. So with that, it is time to code. Here, and I think I'm going to stop sharing for a moment. And let's see. I need to reshare my screen, but do it in such a way that I can share my whole screen. So let's see if I can do that. Okay, entire screen. Okay, let's see here. Oh no, it's not gonna want me to do that, but that's fine. We'll kind of just work with this for now. Okay. Maybe a window. No, I had to do the Chrome tab. Okay, we'll work with this. Okay, so here, I'll just be kind of switching between screens as we go. So we'll kind of go through things on the fly. So first, again, on the toolkit, you'll see this intro section, the orientation section that our team over many different years have produced, and there's additional resources that you can check out. And we're going to start with this intro to spatial data section. So this is something you can also work on kind of in more detail on your own time. Uh, but let's first set up our working environment. So we're going to bring in the SF library and the TMAP library. And we're going to also want to bring in Chicago census tracts so we can see that information right here. So I'm going to copy this, and let's see. This will be a little bit of a challenge, which is nice. I think this is the fun part of live coding, is you see what can work. Okay, so here I'm going to load in SF, and I'm hitting command and return so that just that line is run. That seems to work a little bit better for me. Okay. And then we are going to read in Chicago census tracts. Okay. And that is running. And here we can already do something. So let's look at try tracks. We can look to see what that looks like. So I'm using just a head function, which is a base R function. And when I look at the census tract data, the first 6 rows, what do I see? We see regular data. This data is coming from the Chicago Community Portal. So as open data goes, it's sometimes a little messy. So we have community area numbers shown twice. We have the census tract ID, a note column which has nothing, and then this last column, the geometry column, and this is where the magic is happening. So we read in a shape file, which is actually a suite of files. All 4 files minimum have to be there before they can be read in. And then we are reading in, so we read that in, and now it is no longer a shape file. It is a simple feature collection. We have polygon data. There are 6 features. Oh no, we're just looking at the first 6 features. Let's actually look at how many tracks there are. There's 801 census tracts. And what's really neat is because SF is connected so well with R, we can also plot our data set. And here we'll see the first 10, in this case, there's only 9 columns. So we'll see this information being plotted. So these are all the census tracts in Chicago. So let's go back to our section here. And so we've already done a spatial view and the non-spatial view to look at our information. And we've looked a little bit at the structure. So we've identified that it's both, or it's an SF object, but it turns out that it's also a data frame because, again, spatial data is regular data. And next up, we can inspect the coordinate reference system. So let's do that. Oh, I'm getting an error that tracks was not found, and that's because I don't have tracks, I have tri-tracks. Awesome. So here we can see that
I
it's
think you
using
didn't switch to the code
oh,
side.
oh, thank you,
That
I
works.
appreciate it. Got it. So here, for the coordinate reference system, I had typed in tracks, and it tells me there's an error, but no worry, we're going to go to this instead, and here we can see that, um, there's a lot of information here, and one of the most important things to note is that our unit of distance is a degree. So we can't use this to calculate distance for anything because it's not going to give us very much meaning. So in this case, we're going to try transforming to different projections. So I'm going to just copy this and bring this back in here. And in this first example, this is a mole-wide projection, and you can Google that to get more information about it. But this is actually what Chicago actually looks like on the globe. It's a little bit, when we get raster data, it tends to look like this because the Earth is curved, and this is kind of the shape of Chicago from that perspective. All right. It seems if I, okay, we'll go there. So here we're transforming the census tracts, and how you transform is you just input a new code into the CRS section. And what's special here is instead of an EPSG code, there are other databases. So in this case, we're using an Esri uh, code, and this is just how you input it. So you're never going to memorize how to, what to input. How coding works is you first, try a lot of examples, and you have your encyclopedia of scripts that you go back to and update over time. So here we take our Chicago tracks and we apply this new coordinate reference system. And at this point, this is not my favorite or way of mapping things. So at this point, just worry about plotting it the way that it's being shown. We're going to move to a better way of mapping things in a little bit. So here we can see the mole-wide projection. And if we look at the coordinate reference system, we can see that here the distance between two things is going to be a meter. So if we wanted to work with kilometers or meters, this would actually be a much better option to work with. Next, we'll work with the Winkle coordinate reference system, and this is a compromised projection, which means that there's a little bit of error across all things. I'm going to just copy and paste that, and let's see how that works. And so here again, we can see minimal distortion and kind of going with that. But again, with mole wide, we preserved area. Here we preserved some distortion. And now I'm going to show you what happens if you do something that's completely wrong. So if I were to look up a projection that in Hawaii and use that here, and that's what I did in this case. And again, this is also using the Esri database instead of the EPSG one. If I were to do that, let's see how that would work. So we know Hawaii is on the other side almost of the hemisphere from Chicago. If I were to plot that, I would get a completely turned around projection. Okay, so this is very clearly not the way to work with. Um, that being said, uh, what are we going to do for Illinois, right? So let me, oh no. So if you were to Google EPSG, uh, Illinois feet and hit enter, I don't want to reload all of this so that we keep on track. Um, if I were to do that, it is going to give me EPSG 3435 as one of the top recommendations for working with spatial data within the Chicagoland or within Illinois. It's specifically optimized for working with data on the east side of Illinois. So here I'm going to transform my data again. I'm going to use an EPSG code, and I'm going to map that down here. And here we can see Chicago. So this is a data set that's often used, or this type of projection 3435 is commonly used for mapping topographies, for survey usage, and that sort of thing. It's really optimized to measure things very well at a very hyperlocal scale. So where you are in the world, you're going to want to find an optimal coordinate reference system that does the same kind of thing. Okay. And another thing to note is when you're working with EPSG codes, some of these are so well known that you could actually just, so the input here is not just tracks, but it might also be a number. So if I were to do this, it also transforms things correctly. And again, I can see here all the information. I've got a US survey foot as my unit of distance, so I feel really secure about that. And there's all the other information. And just to confirm, it doesn't change anything. Again, we have there's two different ways to input your tracked information there. And that's basically the overview of coordinate reference systems. At this point, you're able to keep on going through the tutorial. You can write the data, and we're going to end with just about 1 minute of mapping the basics. So I already told you that I don't recommend working with a base plot function too much in R when you're mapping because it's not really optimized to do all the things that some other packages can do. So we're going to be working with a library called tmap to do our mapping. And this is where we can start to do things like overlays and all that other good stuff. Here we're going to map. So whenever you're mapping with tmap, it will take two functions for every single thing that you want to map, for every layer that you want to map. So here we have Chicago census tracts, the 3435 projection that we just did. We want to use that as our base shape. And then we need to tell tmap how to style that. So here I'm going to say, give me borders with a line width distance of 0.5. So let's see how that looks. And yeah, so we're going to map that. And we can see what that looks like right there. So if you weren't sure what LWD did, experiment, play. So here I'll try line width 2. We can make it much bigger, which is very not pretty at all. Another option would be going the other direction and making it a very light background. Okay. And so we can keep on going. And here we're making a slightly prettier map. And this might be what's called a reference map, where we have our area, but then we also will add a scale bar on the bottom left side of the map. And we just turn off the frame. And so this is, again, a very simple map. We'll be going through more complex maps as we go through. So in this case, I'm still mapping the same shape. And now I'm using a function called TM polygons, which is the workhorse of tmap. Tmap just changed to version 4 this year, and there's a lot of changes that have come with that. So be really careful when you're working with tmap to know which version you're working with, just in case because you want to make so because some things have changed, so they won't work the way that they might have once worked before. So here we're going to change the fill color. We're going to give the border color a different name. We'll change the line width, and then we'll also give a nice scale bar. And here we have that map. And with that, I'll just show at the very end of, let's see here. Oh, sharing this tab. Yeah, so you can see this tab right here. So at the very end here, you're able to see a couple more references. Again, this first chapter is probably the hardest just to jump into because you have to start to understand a lot of things. We're not doing that much coding at the very beginning, but we're trying to improve our understanding. So if you have more interest in any of these topics, there's a bunch of resources here. But with that, we're going to pass things over to Yilin to take us through geocoding.
Hello, everyone. Can you hear me? Okay, so let me share my screen first. Can you all see my screen right now? So after understanding the fundamental ideas and operations of spatial data in R, we are going to move to the next section of geocoding. So let's start with a quick introduction about geocoding before we actually start writing the code. So what is geocoding? It is a process of converting address into geographic coordinates using a no coordinates reference system, which we refer as CRS. So we can then use these coordinates, including both latitude and longitude, to spatially enable our data. So like during the geocoding process, we will first have the input as a text format address, and then after we finish the geocode process, we will have the output that including the information of both latitude and the longitude coordinates. So we've simply divided the geocoding process into 4 steps. I will go over the entire step briefly, so give you a sense about how the entire process look like, and we go through the live coding section step by step. So the first step of geocoding will be reading the data. So we will use the read function to read CSV files and store it as a data frame, which you consider it as a spreadsheet inside of R, including rows and columns, just like Excel. And after you read the data, we always recommend you to do a quick check whether the data has been imported correctly or not. So the second step will be prepare and geocode the data. So we will use the geocode function to which takes our address in the dataset and return back with the latitude and the longitude information. So as you can see here, will be the 2 output columns, including the both latitude information and longitude information. So after we having the coordinates values, the third step will be convert our data into a spatial object. So in this case, R will know how to handle it on a map. And after this, the final step will be visualization and mapping our result. So because for now, all the address has been cleaned, geocoded, and spatially enabled, so they can be added as a point layer on the map. So as you can see on the right side over here, these black points on the map are the clinic locations come directly from the coordinates we generated in the earlier steps. So after give you a sense of how the entire geocoding process look like, we're now going to the live coding section. So let me switch to the R. So I will use, so all of the code in here is exactly the same to what we have in the toolkit page. So I just copy all the code here so we can do not switch different pages. We can just focus on this page to run the code line by line. So in the beginning, for every type of geospatial analysis, we need to set up the environment. We need to do the environment setup, which Marinia has already covered for how to install packages required for this workshop, and also prepare the example data we have. So for the geocoding section, we're going to use four libraries. Three libraries. The SF library for handle spatial data, and a tidy geocoder, which helps to turn our address and into coordinates information. And finally, we will use the T-map for the last step of visualization and mapping.
Oh, Yilin,
So,
there's a quick request. If you try doing Command plus to increase the size of the code a little bit,
oh, okay.
I think that it might be small for some people to see. Okay.
Is that better?
Yeah, I think that works.
Okay.
Thank you.
So we need to first loading this required libraries before we start the analysis. So I just click, you can also click on the run button here to run the code of every line. So we just run the 3 line here. And then after loading the library, we're going to load the data. So in the geocoding, we're going to use the Mastodon Clinic data. So we use the read CSV function and tell the R which folder you store this data and which data you are going to read. So here we use this function to read our example data and store it as a data frame called Mastodon Clinics. So there are two methods that you can check how the data looks like. The one method is just Marinia showed, we can use the head function to see how the data looks like. So it will give you the first couple row of the data you can see here. But another way is also the way that I personally prefer is you can go to the here environmental tab, and if you just click on the name of data, you will see it gives you a table format of data, which is relatively like more clean and straightforward to see what rows and what columns your data have. So back to the code. After we load the data, we will start with the geocode address process. So we always recommend you to check your data before doing analysis to make sure there's no major issue in your data. For example, like spelling issues, or if your data missing any important information, for example, like the zip code information. And also you need to consider how to selecting the geocoding service. So in our practice, we're using the tidy geocoder, which connects several geocoding services like OSM, Google Maps, US Census Geocoder. They are all operating the same things, like turning the address into coordinates information, but they are different in some aspects, like their accuracy, speed, and whether they are require API keys or payments. So, and also you need to consider the data privacy of your data used, because if you are using the privacy data, you may avoid using online services. So instead, you will need to use some offline geocoder services. So we're not going to cover too much about how to select the geocoding service here, but more information has been included in our toolkit page. So we also include some useful links on the toolkit. So if you are interested in how to select geocoding service, you can find more information on the toolkit page. But here, we want to first do a test for the geocoding, so which may help you to understand how the input and output should look like. So we just use this line of code to geocode. So for this sample, we're just trying to geocode this address into latitude and longitude information. So if we just run this line and check how it looks like, it will look like this. So we will have the text format as the input of our address, and then for the output, we will have two columns, one column for latitude information and another column for the longitude information. And after we have a sense of how the input and output looks like, we are going to officially deal with our example data of methadone clinics. So before we run the geocode analysis, we need to make sure all the input address are correct or are formatted well. So we need to first check the data structure of the methadone clinic. So we use this function to check the data structure. You will see some of the columns, they are stored as character, and for example, the zip code is stored as integer. So for the geocoding function, it needs a single combined address string just to look like the example we give here. So we need to combine all the components like address, city, state, or zip code area together into a complete address string. So in this case, we are going to create a new column to combine all these components together. So here we use this line of code to tell the R, in the methadone clinic dataset, we're going to add a new column called full address. And within this new column, we're going to combine all this component together, including address, city, state, and zip code. And during this process, we are going to use the as_character function to convert all the data in consistent as the character information. So we can just click on run this line of code and then check the detail. You will see the new columns has been added at the end. So if we see in this format, you will see here is the column we just added. So you can see all the address has been combined together from the previous components. So this column called full address will be our input for the geocode service. So now after we have checked our input of address, we can batch the geocoding for the entire dataset. So we are going to use the geocode function, and we tell the full address column it will be the input of our geocoding, and we expect it for the latitude and the longitude as the output, and we are using the method of OSM. So if we just click on to run this, so it always takes some time to run the geocode service. Sometimes it may take several minutes, especially if your data is really large. So you need to always be patient about waiting this process to be complete. But if you get when you get your result, if you found there are any NA values or empty values, that means there's something wrong in your input address. Maybe some spelling error, or maybe you missed some important information. So in this case, you need to go back to fix your input parameter and then go back to run this geocode code again. So now we have successfully run the geocode, and we can check how it looks like. So as you can see here, we have the output of this two column, latitude and longitude information. And if you remember, we discussed in the slides, there is one more step before we do the final visualization of the map, is we need to convert our data into a spatial data frame, so R know how to deal with this data on a map. So in this case, we are going to use the STSSF function to convert our data into the spatial data frame. So we are operating with the data the geocoded clinic data we just generated from the previous step. And the course argument specifies which two columns are the X and Y of your data, which are the latitude and longitude. And also we set the CRS to 3322 here. So if we run this line of code, we have successfully convert our data into spatial format. So if we open this table to check, you will see there is a column called geometry, which you can see all the address has been converted to spatial points, which include all the latitude and longitude information here. So You can also use the head function to check over here about this new geometry column. So the final step will be visualizing our point on the data. Oh, sorry, on a map. So we are using the tmap function with this line of code. So the tm shape defines the spatial object that we want to plot. So here we want to plot the spatial data frame we just created. And we use the tm dots function to add points to our map. And also we use the tm base map to add a background map. So in this case, we can see where those clinic points are located in the real space. So we can just run this line and you will see here is the final output of the map. You can zoom in and zoom out to explore where are the black points, which represent for the methadone clinics in Chicago. And after we have visualized the map, there is a step to save our data, like save the points data as a shapefile. So we use the write asset function and to store it to the folder, whichever folder you prefer, and store this data as a shapefile format. So we just click on run. And if you go back to, let me see. So if you go back to the data, you will see here is the data we just imported, the shapefile format of the clinic points data. So that's all for the geocoding part, including how the entire process and what code we can do to achieve this goal. So the next step will be like after we have spatially referenced the clinic locations, we will move to the next section about buffer analysis. So the buffer analysis was used when we are interested in events or features that happen near our area of interest or within them. So it also can be used for visualizations as well as to make some new measures, for example, the count of buffers or area covered by buffer. So you can consider this as a process of drawing a circle around a clinic, for example, and find out what is near the clinic. And here we suggest you to think about the spatial process of your phenomenon to see if it cares about the existing borders. Because, for example, the phenomenon of people traveling to the healthcare resources like methadone clinics, this kind of phenomenon do not always fit neatly within a fixed boundary because people may go into the clinic or healthcare resources which is not in their zip code area. So in this case, the buffer analysis helps a lot. But also, there are some considerations we need to keep in mind when we calculating the buffer. So the first one is we need to use a coordinates reference system that use an appropriate unit of distance. As Marinia mentioned a little bit before, we need to use the CRS that measure miles or feet, but not the degrees. For example, the WGS 84, which is measured in degree, so that may be not appropriate for the buffer analysis. And the second thing is about how to select a meaningful distance of the buffer, for example, 1 mile or 10 mile. So the truth of this threshold requires you to think about like what makes sense to your research question and what makes sense for the real world behavior. But this kind of threshold can always be informed by doing some literature review surveys or best practices. And also another thing to consider is you need to think about what type of transportations people are going to use to access the resources. So if you are seeking for the walkable distance, maybe 1 mile or half mile under the urban context, but if you are focusing on the population who using their own vehicle or public transportation, we may need to increase the distance from 1 mile to 10 miles. So the next thing is about, we often say that buffer serve as a container technique, which means we use them as a spatial container to summarize or analysis features that fall inside the container, for example, like a zip code area. But one of the benefits for the buffer analysis is it is useful because it allows us to move beyond the rigid administrative borders. So as you can see here, with two examples, if we just count based on the fixed boundary, we can only count one methadone provider in this green area. However, if we are using the buffer analysis, we can consider two providers within this area, even though this black point is outside of the boundary, but it's easy accessible to the people who live in here. So other than its like the benefits or the advantage of the buffer analysis, there also have some questions we need to keep in mind. The first question will be the sensitivity of boundaries, because sometimes a tiny change in the boundary will can change which side of the provider falls in. And the second question is about how to pick the right distance. So the right distance is really depends on the place and the population your research focus on. For example, your research is focused on the under the urban context or in the rural area. And the third question is that buffer draw perfect circles, but in our real life, people don't travel in straight lines. We move along like street networks and along sidewalks. So this may be sometimes simplify the real world situation. And the final question is to think about the transportation types people are going to use, because not everyone gets around the same way. So we can say that buffer are a great starting point, but sometimes they may simplify the real world situations. So as you can see here, we provided two example maps of Chicago, both showing the provider locations using black points. But the left map over here, we use a simple count, show where the clinics are. Oh, sorry. However, in the right side, the green map use a buffer analysis showing where clinics might actually be accessible to residents nearby. So we can see the difference between these two maps highlights how buffers can actually help capture proximity, not just based on the fixed administrative boundary. So after like a brief introduction about what is the buffer analysis and its advantages and the limitations, we will now move back to the live coding section about to understand how we can write code to create buffers based on the location points. So let me just pull back here. So for the buffer analysis, we started with the theme scene, the environmental setup. But since we have already did this in the geocoding section, including install packages and loading libraries, so we're not going to run this two line of code again. But for the buffer analysis, we are using two libraries, the SF and TMap. And for the data we are used for the buffer analysis, we have two data. The first data is the methadone clinic location we just created from the previous section of geocoding. And in the last step, we store it as a shapefile. So we will use that data in the buffer analysis here. And the second data is the zip code polygons in Chicago. So for both of this data, we are using the stRead function to read those. So we just click run to have this two data loaded and use the head function to check our data. So if you check the area data, you can see the geometry column. It shows a multi-polygon, which is slightly different compared to the to this one, because this one is the clinic points, which are two different type of spatial data. So back to the analysis. After we loading these two data we need for the analysis, we can just trying to create a simple overlay map showing both of these two data to make sure we have imported our data correctly. So before we plot that, you may notice that the map we made for geocoding is an interactive map, which means like we can zoom in and zoom out to explore. But here for more convenience to view, we just want to change the how we just want to change it to a static format by using the tmat mode function. And if we click on this run this line of code, the following map generated will no longer be interactive, but it will be a static map. So now we can start to visualize the two data we just imported. So there is the entire code, and the first line is the layer of zip code areas. So we use TM shape to define the spatial data set we want to plot. So the first line is plotting the zip code area, and we use the TM polygons to draw polygon features like areas from that layer. And the second layer is for the methadone clinics. So same, we use the TM shape to define the spatial data set and use the TM symbols to plot the point or symbol features like clinic locations. And you can adjust some features here, for example, the border color of the points and the fill color of the points and also the size of the points. So if we run this entire code, you will see here how the map looks like. So in this map, we have the two data set, one data set for one layer for the zip code area and another layer for the clinic points. But for now, we have make sure that our data has been imported correctly, but we also need to check whether their CRS are consistent because if the coordinate reference system are not same for the data, the R cannot run the buffer analysis. So we can use the stcrs function to check what is the current CRS of these two data set. So if I pull up here, you can see for the clinic location, we have the current CRS of WGS84. And for the area, which is the polygon, which is the zip code area polygon, it is currently in the WGS84DD. So they are slightly different. And also, if you remember, the WGS84 measures in degree, but not in feet or meters, so which is not appropriate for the buffer analysis. So in this case, we need to set a new CRS for the further analysis. So here we use the EPSG code of 3435. You can always search which CRS code is appropriate for your research area on Google. Like Marinia mentioned, for example, Illinois CRS in meters or in feet. So here we use the stcrs function to set a new CRS, and we run this line of code. And then we need to use the sttransform function to transform both of our dataset into the new CRS we just defined. So let's run this two line of code, and now we have our dataset transformed to our new CRS successfully. And now we can finally start to create the 1 mile buffer based on each methadone clinic points. So for creating the buffer, we're going to use the stBuffer function, and we tell the R which dataset we are going to operate, which is the methadone clinic points set with the new CRS. And then, since the new CRS we set, it measures in feet, so we just put the value here, which equals to 1 mile, and then we can run this line of code. So we have successfully created the buffer for now. And in order to check how the buffer looks like, we need to map the buffer on the map. So we use the similar function here. So as you can see, here are three lines which represent for separate three layers. The first line is for the zip code area, which is the base. And the second line of code is plotting the buffer we just created. And the third line will be the the Macedon clinic points. So if you run this entire code, you will see how it looks like here. So compared to the previous map, you will see now we have the buffer showing circles within 1 mile service area of every clinic locations. But currently, our map is like relatively simple. We have a blank background and no like map titles or something. So we can do something to make our map looks better. So as you can see here, 4 line of code is just we add a new line of tn base map function to add a base map to our current map. And we still include the zip code area layer and the buffer layer as well as the clinic point layer. But we adjusted a small things here to change the transparency of the buffer area and also the line width. So I can just run this line so you can see how it looks like after we adjusted something. So compared to the previous map, you will see we first add a base map, and also compared to the previous buffer analysis area, you will see we have created some transparency about the buffer area and we change a bit about the line weight. So in this case, we can always make our map better by adjusting some arguments within the function. So for now, we have calculated all the individual buffers, but it is also important to finding out the overlap areas. So in here, we are going to use a union spatial operation, which help us to find areas fall within a 1 mile service area. So the function is called stunion. Oh, sorry. So the function is called stunion. We just run this line of code and then we run the code for mapping using the same structure, including both the base map and 3 layers. So I will just run this and you will see how it looks like after we merge them together. So as you can see, compared to the previous one, currently we have merged all the buffer areas together to see what are the overlapping area and which areas are fall within the 1 mile service area of every Macedon clinics. So now we can use the stwrite function to save our merged union buffer as a shapefile for the future analysis. Okay, so I received this error message because I've already saved this data in the previous practice. Um, for now, we have completed the entire process of how we can geocode locations and also create buffer based on the spatial points. But we still want to do a couple codes to help you get familiar and better understand how this entire process work. So we're going to add another buffer layer to compare the access of Macedon clinics. So here, we just did the 1 mile buffer before, and now we are just want to create a 2 mile buffer using the same structure of code using the st buffer function, and we change the value to 2 miles. And we can just run this line of code, and then we can map the result in together. So as you may already familiar with this mapping code structure, we have the base map here and the zip code boundary here. And also slightly different is that we now have the 2 mile buffer layer, as well as the 1 mile buffer layer together. And we also have the clinic points at the top. So if we run this code, you will see it is how it looks like. And also here, something new is that we use the TM layout function to add a map title called Methadone Clinic Service Area, and we try to put it in the center of the map. So in this way, you will see all the 2-mile buffer and 1-mile buffer are mapped together with the clinic points and zip code boundaries. So as for now, we are using we map the things as a static format. So now we can turn back to the interactive map by using the T-map mode, change from plot to view. So if we click on this and then we run this a chunk of code of visualization again, you will see it turns into a interactive map from a static map previously. So if you zoom in and zoom out, you can see we also change some features here about the transparency and also the color for the buffer area. So as you can see here, the relatively larger and with some transparency circles are the 2-mile buffer, and the relatively dark purple area are the 1-mile buffer. And we also use the TM text function to add the information of zip code text here. So as you can see, now we have a relatively comprehensive map, including all the informations we have. So yeah, that's all the process for how we can turning the text format address to the spatial points and show that points on the map, and also create the buffer based on those methadone clinics to find out the service area. So the next part will switch to Marinia about how we can link the community data with the previous section.
Thank you so much. That was amazing. And I'm going to kick things off by going back a minute, just to kind of take a moment to reflect on what was what are the purpose of all the different things that we're doing. So traditionally, a lot of toolkits out there kind of focus on the methods, step by step, like this is how to do this and this is how to do that. Our approach is more based around the problem again. And so we've started things off with working on like locations of different providers, healthcare providers. Um, so we have these healthcare providers. That's why we were geocoding the locations. And again, I just wanted to highlight again, I added this in the chat, but in case you were working on coding and not seeing the chat, make sure that you're not using an online geocoding service for personal data like medical records, because that is considered protected and you kind of need a different approach for that. There are also a lot of really great questions about what methods are available within the Tidy geocoder system. And there are multiple geocoding services available. So you can review all of them here. It's changed so much just in the past 5 years, honestly. So it's very possible there'll be more. ArcGIS, their geocoder is actually available through this service as well. So there's others, like for example, the Google one can be really great. However, it can start to cost a bit of money after a certain point. So just keep that in mind. And we do add some notes on all of this in the toolkit. But again, as Yelan highlighted, just knowing where things are is not enough. You usually want to do some sort of access analysis or gap analysis. Are these resources available where people most need them? So sometimes we start with a very kind of simple, straightforward spatial view of how are they distributed throughout a place. So that's why we went into the buffer analyses. But next, we're going to shift into when there's a crisis or an urgent scenario, who can access those resources? So now we're going to bring in some COVID data from the first year of COVID in 2020 in Chicago to see. So someone who needs access to methadone, that's a medication that is very complex, requires there's a lot of policy barriers around access to methadone in the United States today. And to complicate things further, that's a resource you might need every day or every month, depending where you are in the process. So if there is a massive pandemic and everything's shutting down, you still need access to your medication, right? So again, there's lots of complications, but we're developing a scenario here just to give you an example of what you can do. So here we're going to bring in COVID data and then overlay those buffers that we just created to see if that makes or what are additional complications that may emerge as people are trying to access their resources, right? On the one hand, if there is a hot spot of infection locally, that might make it more likely that you're not going to go get your resource, right? On the flip side, if you do get your resource and get your medication, you might be exposed to more virus, just by the nature of proximity and how contagion works. So it's very complicated. And with spatial analysis and spatial epidemiology, we're trying to understand the environment a bit more. So that's kind of where things are. Um, and we'll kind of, kick things off. So in this, let's see here, I'm actually going to go back to this tab. Before diving into the code, we need to talk a little bit about what we need to do technically when we're linking community contexts. So when we're linking context of what's happening at the neighborhood level or a regional level, we're actually joining that data to or different data sets together. So combining data from different sources is a very common task in data preparation. If you're a spatial GIS person, it's probably at least 50% of what you're doing. So joins do this by combining tables based on a shared key variable. And so geographic location can actually serve as that key that links different data sets together. Sometimes this is done the easier way, where we actually have an identifier already in the tables. So it's really straightforward to merge. So that's what we're going to work on today. For example, we may have in the US a zip code, which is a 5-digit postal code. You may also have what's known as a ZCTA, which is a census version of a zip code that's relatively stable over time. They're technically different. You could have a census tract identifier or some other FIPS code. So every place will be unique on how that information is measured. If you don't have that information, we can still join based on the spatial information from those two layers. That's called a spatial join, but we're not going to cover that today because it's a little bit more advanced. But that'll be in a future workshop. So by referencing each data set and enabling its spatial location, we can integrate different types of information in one setting. And so what does that actually look like? So if you have two tables and you would like to join them together, um, how can we do that? And this is where the format of that data can be rather complex. So on the top, we see a table of data, and this will be kind of the data we're working with today. These are weekly COVID case reports as they were downloaded from the Chicago data portal. So we have a zip code. Here, the zip code is identified as zip.code. We have a week number and a bunch of data. If we look closely at this data, we can see that zip codes show up multiple times, and that's because every week is a different row. That might sound, that is technically tidy data where every variable is measured as a different column. That is considered the best way to store data in R and the tidyverse and a lot of different data practices. However, that makes it suboptimal for working with spatial data because spatial data uses the wide format where every single zip code needs to be a separate row. And every zip code is a different spatial area or spatial object. And the spatial object of zip codes is, again, this collection of polygons, multi-polygons. So here, we're going to have to change our data, reshape it, or subset and then merge it in order to go and to go further. Because for joins to happen with spatial data, we need a one-to-one match. So here's that same thing on the left-hand side, and on the right-hand side is what we want. We would like for every zip code to have its own row. And what we're going to have to do is, in this example, we just take 2 weeks, week 19 and week 39. There's nothing special about those 2 weeks. They're just kind of randomly pulled from the data set. So we're going to have to take week 19, rename this as a new column. So we'll call it case rate week 19 because we're looking at the case rate cumulative measure so that we're accounting for population. And we're also going to grab case rate week 39. So these two data sets will be we're going to actually take a subset of the data. We're going to rename the variables so that we're ready for a really easy merge. There are more complex ways of doing this. In R, there is something called, in many data wrangling works, there's something called reshaping the data, where you can potentially reshape everything all at once, but that does require, it's a little bit more advanced than what we're doing today. But for those of you who are interested in that, there are some tips for what kind of functions to look for in the toolkit. So we're going to subset the case data so it's ready for a one-to-one join. Then we're going to merge our data with the master spatial data set using our key. And in this case, we're going to actually rename our zip code to zip, but you're also able to merge in R, just assigning what the two different things are. And then finally, we're going to write our new merged data set as a spatial data set. And what's really important with joins is that you should always be merging and joining to the spatial data. If you go the other direction and you merge to non-spatial or just regular data, you lose the geometry information. So this column on the right-hand side, it needs to exist. It only works if it exists as a spatial data set. So it has to be a SF object in R. Outside of R, it needs to be a shape or a geopackage or something like that. So that's just a fair word of warning. And then when you're joining and merging, there's many, many, many different ways to do this. Base R uses merge. We're going to use that today. We're going to do what's called a left join with merge, where we're keeping, so, think of those two circles that are overlapping each other. We've got Chicago zips. We want to keep all of our zip codes and just join the data that matches from our COVID data set. In dplyr or the tidyverse, there are multiple other join functions like left, or that do the same thing but are more kind of explicit in what they're doing, like left join or inner join. That is, there's a really great kind of section on that in that textbook that we recommended earlier. But there's also a lot of resources online about how to work with dplyr and tidyverse. In addition to that, we have this other challenge where if you have a key that's not the same across data sets, either rename the key variable so they match, that's what we're going to be doing today, or use update the by argument here. And if you don't know how to do that, I still will forget how to do that. You just Google it, you search it, you look at the documentation. And this is kind of the direction where we're going. So once we have all these different data sets together, we can create more meaningful spatial visualizations that will give us new hypothesis generations to consider additional data to bring in, and so on and so forth. So this is kind of where we're going. We'll have a case rate measure. We'll overlay those walkable methadone service areas. And kind of from here, already looking at this, you can see that there are differences in case rates across the city. And in some areas, there's going to be very problematic access to healthcare providers if their very, very local community is experiencing an outbreak of a specific disease outcome. Okay, so with that, it's time to code. We're going to just do a little bit of coding, and I'll leave a little bit for you to dive into more on your own, because we do want to get into the final slides. And then for the last about 15 minutes, give everyone a chance to work with each other in smaller breakout groups. I know, group work. Okay, so here I'm going to switch to this tab. And in this example, we're bringing in a lot of different data. So I'm going to just work with the methadone clinic data and our COVID case data, but you're also going to have additional measures that you've brought from previous the previous slides. So the methadone clinics, the 1 mile buffer zone, and that sort of thing. I'll show you how to work with this just based on, if we had started it in chapter 1 and then we want to jump to chapter 4. But again, we leave the additional replication to you. So in this case, we're going to load in a few libraries, SFTMap, but now because we're wrangling data, we're going to be bringing in a non-spatial data workhorse. So that's going to be dplyr, but you can also use the tidyverse. dplyr is part of the tidyverse. And again, either or works. So we're going to load in some data. At the very beginning, we load in a bunch of data, but in my case, I'm going to load in or focus on the COVID data and the Chicago zip data, because I want to link those two data sets. And then from here, we're going to be trying to identify a geographic key. So let me go back here. And this is where we're going, but let's see how we got there. Okay. So first, I'm going to load in my libraries. And again, in this example, I'm just going to bring in the Chicago zip data. I haven't replicated what Yilin just did in this environment yet, so I don't have points or buffers to bring in yet, but I can still link data without that, because that's kind of a separate process, and the buffers we were going to just overlay as a visualization. Okay, so here we've got this data, and whenever you bring in data, you want to look at it, right? So, and here you can see our little global environment. We have a bunch of different data sets. Actually, so I can look at it this way, but I can also look at it by clicking on that data set here. So let's look at our Chicago zip information. We have an object ID, the area of that using some measure that we don't know. We actually don't know what unit measure that is, because it was not disclosed on the website where it came from. And this is our column that we want to merge on, the zip column. And if I look at my COVID data set, here it's called zip.code. And again, we can see that every zip code shows up multiple times, because it's every single week has a different number. And this case rate cumulative measure is the data set we want to pull, so that we can kind of see what, when adjusting for population, where are areas that are being disproportionately impacted by the spread of COVID. And this is, again, we're going to focus on weeks 19 and weeks 13 or 39, 19 and 39, which are definitely, before the vaccine and during those early days. Okay, so we're going to look at that. And so here, and actually I can switch back to here that because it's the same information. So we're going to look at that. And again, we have to switch our COVID data set from the long format to the wide format. And the way that it was shared too, this is traditional epidemiological reporting format, where everything, every observation is its separate. Every variable, or every observation is a separate row, but then every variable has a different column. So it creates this very long data set. I think it's around 1,800 rows of information that are in this. So we're going to identify the column names that we want, because how this information was loaded into R, there's a lot of kind of bizarre things that show up, where we have this ... information. That happens a lot when you're working with data from different data sources. You'll get kind of odd column names and that sort of thing. So we're going to grab this case rate cumulative measure. And here, this is the magic of dplyr. So with one little piece of code, we're going to do a bunch of things. We're going to, from our COVID data set, and this is called a pipe, which is something really special that exists within the R world. We're going to take our COVID data set, we're going to filter it so that we only include data from week number 19. That means every zip code that has a value in week 19, this was going to be our new subset. And then we're going to only select 2 columns from that information because we don't need all the other data. We're going to grab the zip and the case rate. And here we're actually renaming our column on the fly. And again, this is the magic of dplyr. We don't need to do this. We don't need a whole page of code to do this. We can do this in this one little code chunk. So here we filter those 2 data sets. So now we have COVID from 19 and we have COVID from week 39 rather. And at this point, we're going to just merge that data. So we take our Chicago zips file as our master data set. We're going to add week 19. And then we take our merged zip file. And there are better ways to do this, but this was just kind of the most straightforward way of doing it for our workshop. And we're going to do that again here. So now, if we look at our zip data set, this is our brand new data set. So we have the zip ID and all this other information, but now we also have case rates from week 19 and case rates from week 39. Now that we have this, it is ready for mapping. Instead of having 1,800 observations, we still have 60 so there's 61 zip codes that we started with. We're not adding any more zip codes to that. All right, so we end with 61 zip codes, and we can from there do some, let's see here, do some mapping. And here we get a little bit more fancy with the information. And that's because we're going to be doing what's called a choropleth map. And this is going to be the beginning of one of the next workshops that we work on, where we're just going to give you a taste of a choropleth map in this workshop. And a choropleth map is essentially a statistical map. You're taking the data and you're adding different data classification points. You have different buckets or bins of the data. So for example, here we see a quantile map with 6 bins, and the data is being split. So each of these 6 bins will have approximately the same number of observations if the quantile approach is working the way that we want it to approach. So when we map that color-coded, we can get some really interesting insights and information. As we'll learn in future workshops, how you change the bins as well as the different methods you use for breaking the data, it can create very dramatically different maps. So that'll be important. So here, this code produces this outcome. And here we can really start to see healthcare. Like, for example, if this was week 39, I would reach out to this healthcare provider in this zone between these 2 growing hotspots to let them know, hey, folks here may be especially vulnerable to the emerging case rates, and that might have a different intervention than those who are already within those centers, right? And here, because we're going to want to compare 2 different weeks, we're going to want to have a fixed break, like fixed bins that are comparable against that. So in this code, we're going to actually generate breaks like this. So 1,000, 2,000, 3,000, 4,000, 5,000, so that we can see. And here, if I just copy and paste, right now, it's not going to work because we did not load the buffers in here. So I'm actually going to remove these 2 lines, and we're going to just map the data itself. And we can see that right here. So let's move this bigger. And so here we can see that this these fixed breaks are generally not recommended. unless you're trying to do something like what we're trying to do and comparing two things, in a reasonable way. So here we really see the same kind of pattern from the other example that we were looking at. And it's becoming clear that this is going to be a data set we need to, it's becoming clear about what parts of the city are experiencing COVID disproportionately, and that is going to link to how we might do different planning on the ground with different healthcare providers and that sort of thing. Okay. And at the end of this, just to kind of skip to the end of what your final maps will look like, you can see this is, again, all coming from the same data source, the COVID case data. But on the left-hand side, in week 19, COVID had not, was still pretty new to the city and had only reached a couple of areas. By week 39, you've seen it really expand to the rest of the city. And those first areas that were impacted have much higher case rates than at the beginning. So in future sessions too, we'll start to hypothesize why might it be higher in these parts of the city versus others. For that, we're going to have to bring in more data, census data, information about the neighborhoods, information about the populations who live there, and that sort of thing. So with that, I'm going to stop sharing. And oh no, actually here, I might reshare because I think it's time to shift back to our final slides. So next steps. There are going to be a couple different resources that our team will start to share out through emails, as well as through the chat here. We have a new Slack channel that is going to be for the GCCP, but that's going to also include channels where if you have questions about coding, you can drop them there. If you are an open science-minded person and want to help other people who have coding challenges and that sort of thing, also you can support your colleagues there as well. Our goal is not to support every single person here because we want everyone to be independent and working with your own teams and groups to move things forward. We're still here to support in as much as we can, but our goal is to kind of encourage you all to troubleshoot and move forward and that sort of thing. We'll also be sharing future events, talks, opportunities, but we're asking you all to do the same thing so that we can kind of continue to mingle online with fellow spatial data enthusiasts in the health space especially. And then again, our next panel session will talk about opioid geographies, but those of you who are interested in health geographies in general might be interested because we'll have a physician, a geographer, a sociologist, and an epidemiologist talking about how they think about the environments when they're working on those specific topics. And we'll also be having more information on roundtables coming up. And that being said, the toolkit that we shared today is actually the second version of this process. So on our YouTube channel, you'll see videos from the earlier ones, but we are updating a lot of things. So we're going to be combining our census chapter from previous work with a new with additional information about accessing clean data from another project that our team supports. We'll also be having more information on access metric calculations, as well as intro to spatial cluster detection and regression analyses, because we've heard that being something of interest from a lot of folks.